Okay, number 16, start with here, we got, gives us a graph of a function, and it says it's differentiable, and it says the graph has a relative maximum at, or a relative minimum at 1, relative maximum at 5, and it says let g be the graph defined by the integral of this f graph, from 0 to x. And it says here, for what values of x does the graph of g change from concave up to concave down? So regardless of what information we're given, whether we're given a graph or a table or an equation of any sort, bottom line is we know that there's going to be concavity changes when the what of g equals 0 or doesn't exist. And when the derivative of g, does the derivative of g have to do with concavity of g? Second derivative. Okay. So ultimately we want to know then g prime of x from the fundamental theorem we know is just simply f of x. So g double prime then is going to be f prime. So ultimately this is going to change concavity. G is going to change concavity when this equals 0. And there's nowhere it doesn't exist, so we know it's just where it equals 0. So ultimately we want to know when this equals 0. Those are going to be our candidates. So when does the derivative of f equal 0? Well, they told us that there's a relative minimum at 1 and a maximum at 5. So x equals 1 and x equals 5 would be our two candidates. And bottom line though is that not only does the derivative here have to equal 0, which in turn makes the second derivative of g equal 0, okay, but we also have to have a change from this going from increasing to decreasing or vice versa. And since those are maximums and minimums, we do have a change there, going from a negative slope to a positive slope, and a positive slope to a negative slope at 5. So therefore these two would be candidates, but the ultimate question here is when does it change from concave up to concave down? Okay, in other words, when does the second derivative go from positive to negative? Okay, which in turn means when does the slope of this go from positive to negative? So positive to negative would be at the 5 then, wouldn't it? Because at 5 we're going here. So slope's equal to 0. Slope goes from positive to negative at the maximum. Alright. What else? 16 to 20. Taylor? 18. And 18 we have derivative function here. We got d dx of x to 0 of du and then 1 over u squared. And alright. So ultimately we want to know essentially what is the derivative of this function. We don't need to anti-differentiate necessarily because we just want to find the derivative. Okay, the issue we have though is that the limits are reversed. So one of our properties though is such that we could make it negative and switch the limits, couldn't we? And just like we can factor a negative out of an integral, we can factor a negative out of a derivative also, remember. We can just take the opposite of d dx of 0 to x of 1 over 1 plus u squared of du. And then that part right there is simply just 1 over 1 plus x squared. It's just the integrand evaluated at the upper limit. So remember, there's no differentiating to be done, no anti-differentiating. We have the derivative of the integral function. It's just the integrand evaluated at the upper limit times the derivative of the upper limit, of course, but there's no derivative, just 1, so that doesn't come into play here. And again, the negative part just stays out in front, so that should match up with one of ours, hopefully. Looks like letter B. Next. Go ahead. And 19, they give us a table here that has function values and derivative values on -2 to 10. It says the function is differentiable, and it gives the values for f and its derivative, blah, blah, blah. And so on the directions we have to do here, this is the line tangent to the graph of f and parallel to the segment between the endpoints of f intersects the y-axis at what point? Alright, so bottom line here is whatever the picture looks like here, it's somewhat of a mean value theorem issue here because we have our derivative and the slope between the endpoints they talk about here. So if we calculate that slope between the endpoints, we have -2, 26 is our one point, and then 10, 2 is our other point. So those are the two endpoints. Okay. And so if we calculate that slope between the endpoints, we're going to get 2 minus 26, and then 10 minus -2. We're going to get negative 24 on top, 12 on the bottom. Non-calculator part conveniently is negative 2. Fairly nice to work with. Okay. All right, so we know the slope between the endpoints is that. Okay. Now the question is that ultimately we're trying to find an equation for a line here because they want to know what's the y-intercept of this line that's in question. Okay. So essentially we need to figure out the equation for the line that we're looking for here. And remember, the line that we're looking for here is the line that's tangent to the graph. Okay. And it has the same slope as the slope between the endpoints. So we already know one of the blanks, then that has to be the negative 2 right there. Okay. All right, the question is, where is that going to occur then? At what point? Well, if you look at the chart, what do you notice about the derivative chart down there? There happens to be a what? There happens to be a negative 2 in the chart, isn't it? And the derivative is equal to negative 2 at the point 423. True? So there's your x and y. So y minus 23 here, x minus 4 here. So there's your equation for y. And ultimately, or your equation for the tangent line. And the question is, we want to find the line tangent. Where does it intersect the y-axis? So bottom line is, if we just put that in slope-intercept form, we'll be able to see the y-axis one, or the y-intercept, I mean. So if we go y minus 23 over here we get negative 2x plus 8. If we add 23, we get y equals negative 2x plus 31. And is 31 an option? That should be letter C. And that'll do it. Questions on that one? Anything else 16 through 20? Yep.
20.
Okay, and 28 says at each point xy on a certain curve, the slope of the curve is 4xy. Curve contains the point 0,4, then the equation is what? Well, ultimately in disguise here we essentially have a differential equation given. They gave us the derivative. Okay. And if we want to find the curve that it came from, then we need to solve this using separation of variables. Okay. So if we go 1 over y dy over here and we go 4x dx over here, ln of absolute value of y, this would be 2x squared plus c over here. Remember they gave us an initial condition, which was 0,4. So if I do put in 0,4 here, I got ln 4 on this side equals c. So I got ln absolute value of y equals 2x squared plus ln 4. Compose both sides with our e function. Get y here. And remember what we want to do when we have these e to addition power, if you will, separate that into two parts. Remember, e times e, we'd add the power, so we can unadd them back to this step if we so choose. And we always want to do that, especially if we have some kind of natural log in the argument here, because ultimately a natural log and e are going to cancel each other out and just give us a 4 here. So it'll just be simply 4 e to the 2x squared, which corresponds with letter C. Questions on any of the steps there?
Why don't you plug in 0 for no.
That's why. 0,4 was the point, right? Not 4, 0. So remember, 0 in for x, 4 in for y. Anything else on this one? Anything else 16 through 20? Next group, 21 to 25? Maybe? 21 says the equation of the tangent line to the curve y equals x cubed minus 6x squared at its point of inflection is, well, ultimately our answer here is going to look like this again. We need to write the equation for a tangent line. So we're essentially filling in the blanks. We need to know a point, we need to know a slope. And so ultimately, in the equation for the line tangent to this curve at its point of inflection is, well, let's find that point of inflection first. We know that if we differentiate here, we're going to get 3x squared minus 12x, and then if we go 6x minus 12 here, set the second derivative equal to 0, we're going to get x equals 2. So that means that a third of our work is done. We know the x. We can find the y by plugging the y, the 2 that we just found, into the original equation. That'll give us the y value for this function. And so if we put a 2 in there, we're going to get 8 minus 24. Got 8 here, 2 in here, give us 4. 4 times 6 will give us 24. So 8 minus 24 would be negative 16. So that would be that so far. And then ultimately we need to know the slope of this line. And the slope of this line is just going to be the derivative at said point, isn't it? So put our point in the derivative, we'll get our slope. So if we put our 2 in here, we're going to get 12 minus 24. 12 minus 24 would be negative 12. And the answers are in slope-intercept form, so we'll need to change the form here. And if we subtract 16, we get negative 12x plus 8. Yeah, letter A.
Wait, where'd you get the slope?
What gives us slope?
The part of that.
Derivative at that point. Yep. So the slope of the tangent line is just the derivative at that point. Anything else on 21? What else? Here, or adjustment. 23. Alrighty, 23. We have which of the following are properties of a definite integral? So really nothing to write down here. So if we look at our properties here, let's see what they did here. Number one, they did number one. They had a constant multiple, and they took it out in front. Is that okay? Yeah. Sure. This one, they had an x out here, and then they took it out front. Is that okay? No. X is not a constant multiple. You can't take an x and pull it out in front. What about this one? If we go from A to B, is that the same as going from A to C and then C to B?
Yeah, negative.
Sure. So therefore, it would be 1 and 3, letter C.
Wait, what was your other two?
You can't take an x out. You can take a constant out, but you can't take an x out. So you can't just pull a variable out of the integral. Next. Go. 22, we have, it says k is between 0 and pi. We're going from 0 to k of cosine 2x dx equals a half. And we want to know what is that value of k. Well, ultimately, if we anti-differentiate here, which we certainly can, we would get 1 half sine 2x, be our antiderivative of that. The antiderivative of cosine kx is always 1 over k sine kx. Again, if you can't remember, do your, try it and make sure this differentiates back to this. If you were to differentiate that, you'd get cosine 2x times 2, and the times 2 would make the 1 half go away, and you'd have that, which is simply cosine 2x. Alright, so with that, we'd have a half sine 2k. 0 in here is going to give us sine of 0, which is 0. So ultimately, that right there is our sentence then at this point. 1 half sine 2k equals a half. And if we multiply by 2, we're going to get sine 2k equals 1. Multiply both sides by 2. Alright, so if that's the case, if I go sine of 2k, the question is what's going to give me 1 here for sine? Is it going to be pi over 2? Pi over 2 would be, but again, if I can't put a pi over 2 in here and get that, I'd actually want to put a what? I'd actually want to put a, ultimately the argument needs to be pi over 2, so that means that k would need to be pi over 4 to make that happen. Okay. And that corresponds with B. What else? Go. 25. 5, it looks like an implicit differentiation problem because we got x squared and y and x squared equals 6. We went on the second derivative at 1, 3. So recognize that we have a product here with these two. So if we go first times the derivative of the second plus the second times the derivative of the first, that would be the derivative of that x squared y term. And if we do the same thing with this one, we do the first times the derivative of the second plus the second times the derivative of the first. And on the right hand side, the derivative of 6 is 0. Right? And if we collect the things that have dy dx with them, we'd wind up with 2x squared dy dx on this side. And these are both 2xy's, so we'd ultimately have 4xy. And if we divide that, we get dy dx negative 4xy, 2x squared. And from there, that would be our derivative. Right? So once we have our derivative, though, now we need to find the second derivative. Okay. So with our second derivative, yeah, absolutely. So gone and gone, so ultimately negative 4y over 2x, I guess. Make it easier to deal with.
You like negative 2 over x?
Add, yeah, how about negative 2y over x? There we go. Alright, so if we simplify it, obviously it's going to, the more we simplify, the easier it's going to be to find another derivative of it. So if that's our derivative, then we do quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And then here's where we need to, anytime we've done implicit differentiation and finding the second derivative, that dy dx right there needs to get replaced with what dy dx is equal to, found in the first part of the problem. So we get x, negative 2 times negative 2y over x, minus negative 2y in here, over x squared. And you can simplify this if you want to. Ultimately, we're finding a numerical answer here, but we just need to plug numbers in here and do the math. So our point in question was 1, 3. So we got a 1 here, 3 here, 1 there, 3 here, 1 here. So if we do the calculation here, in this part we got negative 6 and negative 2, so we'd have 12. Be plus 6 here, all over 1, so it'd be 18. Questions on any part of the work of that one?
At the very beginning, can't you just factor out the x squares?
You could, and then you'd still have the product rule issue. I mean, you'd ultimately wind up with the same thing. I mean, if you took an x squared out, you know, ultimately you'd have, yeah, you'd have 2y, because you'd have y plus y left over. Yeah. Actually, as a matter of fact, couldn't you just add those together and just get a 2x squared y in the first place? I mean, ultimately, you just would only have to do the product rule once instead of twice. And so, yeah. What else? Mike? Save that one for a minute. Anything else before we move on to the last 5? Okay, and 26, next part. Says that the base of the solid in the region bound by the line x plus 2y equals 4. So we got this line and the coordinate axes, and ultimately, if we solve this here, we'd have negative 1/2 x plus 2. We subtract x from both sides and then divide by 2. So we'd have a plus 2 here, down 1 over 2, down 1 over 2. So we ultimately have that shape right there, which has a 0, 2 and a 4, 0 intercepts. Alright, so that's our shape. And it says, what's the volume of the solid if every cross-section perpendicular to the x-axis is a semicircle? So if we go perpendicular to the x-axis to draw our slice, and we have a semicircle as our shape that's coming out of the paper at us, then we know that we're going to start with our general formula here for that semicircle. We know it's half pi r squared for any semicircle. Alright, and then from there, let's see if we can write an expression for r. Well, r here, keep in mind here, if you use just the function, right, the function itself, that distance right there would be not the radius but the diameter. Right? So ultimately we would have to write 1/2 pi, and then in here we'd have to have half of this. So it would be a half times negative 1/2 x plus 2, all squared. And again, we have to have that other half in there because if we just use the function only, it would be the diameter. We don't want the diameter there, we want the radius. Alright, and from there, we integrate on 0 to 4, and we can see that there's some simplifying to be done here because we're going to have to do this by hand because it's on the non-calculator part. Okay. So simplifying wise, we'd have in the parentheses negative 1/4 x plus 1. We could take the half pi out in front. So we'd ultimately have negative 1/4 x plus 1, all squared. And if we're going to do the antiderivative here, I'd probably just expand it and get negative 1/16 x squared minus a half x plus 1. So we write that twice and FOIL it. Negative 1/16 x minus a quarter makes minus 2/4. Oh, yes, thank you. And yeah, those two would be negative in the middle. Good. Yep. All right. So we have 1/16 x squared minus a half x plus 1 dx. Right. And if we go ahead and anti-differentiate here, we get x cubed over 48 minus x squared over 4 plus x on 0 to 4. Still have a half pi out in front. And the 4 in there would give us 16. So 16 would give us 16/48 is a third. And then 4 in here would give us 16. 16 divided by 4 would be minus 4 plus 4. Convenient. And the 0, 1 is all zeros because there's all x's in all those terms. So bottom line is 0, we get a third. So we get 1/2 pi times 1/3 would be over 6, and that's not right, so something's wrong.
I have to square your anagram.
What did we, yeah, that's what I did here. So half pi r squared, this is our radius.
Now we're finding the volume in the area.
The integral makes it a volume, though. So we're ultimately finding the area of our shape. Integrating it on 0 to 4 gives us the volume. Let's see. We're missing something here. We got a sign wrong or something. We got. That's good. That's good. Plus 1.
The answer's 2 power 3.
How'd you get from +1 plus x?
Antiderivative of 1.
Oh.
So 3 squared, so this is x squared over 2 times 1/2. That's good.
4 cubed over 48.
Oh, 4 cubed. I squared it. That's why. There it is. Okay. 4 cubed, then 64. That's 64 over 48 would be, yeah, it'd be 4/3. 4/3. So 4/3 would give us 4 pi over 6. There we go. See, I knew it had to be some kind of arithmetic error somewhere in there. And we did all the calculus part right. There we go. That's better. So 4 cubed, not 4 squared. All right, good. All right, any questions on the technique and setup, solving part? All right. What else? 26 to 30. Okay, 27 we have a particle that moves along the x-axis, and we have a position function given. Is that? And it says for what values of t is the velocity of the particle increasing? Okay. So keep in mind that if the velocity was increasing, okay, think about the velocity graph. If the velocity graph was increasing, okay, that would mean the what is positive. Not necessarily. I could have, if I drew a velocity graph, it could be increasing and below the x-axis, couldn't it? So if the velocity is increasing, then what other quantity has to be positive? Wouldn't the acceleration have to be positive for the velocity to be increasing? So that means that when we do our work here, we want to find A ultimately. So if we find the velocity here, we can use the product rule. So t plus 1 first times the derivative of the second be 3t minus 3 squared plus t minus 3 cubed times 1. That would be our velocity equation, t plus 1, 3t minus 3 all squared, plus 3t, or not 3t, but t minus 3 all cubed. Alright, and one thing I would do here at this point is to, I'd factor out a t minus 3 here out of these two terms, because keep in mind we have 1, 2 parts here. To make our work simpler, if we factor out a t minus 3 squared, and if we did that, we'd be left with t plus 1 times 3 times t, just 3 I guess, sorry. And then with that we'd have plus, and then t minus 3 here. You don't necessarily have to do this. You could find the derivative of this as such. Just find the derivative of this using the product rule again, and that one you don't need the product rule, but
That last t minus 3 cubed.
remember it was cubed, but we took out a square to remember, so now it's just t minus 3. And that way I'd have in the parentheses, I'd have, this would be 3t, and then 1t, there'd be 4t in here. I'd have 3 here, and here I'd have negative 3, so actually it would just be 4t only. So I'd have 3t, and 3, and here I got a t, and a negative 3. So the 3's would cancel out, we'd leave us with 4t. So that being our velocity equation now, we want to find the acceleration equation. Product rule again, so t minus 3 squared times 4 plus 4t times 2 times t minus 3. And bottom line is we need to know when this acceleration is positive, right? So if we were to expand this, we'd have t squared minus 6t plus 9 times 4. Over here we'd have, this would be 2t, be 8t squared. This would be minus 6. Here, minus 6 times 4t would be negative 24t. And if we put this stuff together, ultimately our final quadratic equation, we have 12t squared. These two would make 6, and negative 6 and 4 make negative 24, would be negative 48t. And these two would make a 36. So if we want to find the zeros of that, we can find in turn where it's positive and where it's negative. So I factor out 12 first, we'd have t squared minus 4t plus 3. And like most calculator problems, that conveniently factors. In this case it would be t minus 3, t minus 1. So if we put those on a number line, 1 and 3, and test them in our second derivative, which is ultimately right here in front of us. And we know that this being quadratic, that it's a parabola that opens up, so therefore this better be positive, negative, positive. We have 2 zeros. And you can test if you want to put a number in there, like 0 for instance would give you 3, which is positive. If I put a 2 in there, that would give me 4 minus 8 plus 2, be negative 1. Anything bigger than 3 in here, like 4, is going to give 16, minus 16 plus 3 would be positive. And then finally, the question then is when is the velocity increasing, it says. So here's our analysis right here. Which one does that match up with? Less than 1, greater than 3. Matches up with letter D, doesn't it? Questions on that one? have this term plus this term is the velocity, right? They both have a t minus 3 in common. In fact, they have a t minus 3 squared in common. So if we pull that out in front, then what's left is going to be what we factor out of this. So there's going to be a 3 and a t plus 1. That's right here. Okay. And then out of this, if we factor a t minus 3 squared out of that, we'll be left with 1 t minus 3 only. Okay. And I just crossed that out because I wrote something wrong. But ultimately, distribute that and combine like terms, you just get simply 4t. What else?
Say like you did factor out the 2 plus 3 squared, could you, like, and you just did it the other way, could you move like that 3 for the units you wanted to move the 3 out in front, or does it have to stay?
Well, you could just you could make this 3t plus 3 if you wanted to. You could multiply that 3 into this parentheses if you wanted to. Remember, this is all just multiplication. This times 3 times this. So that 3 can go anywhere you want. It's commutative property. So, you know, had I not done that, I probably would have multiplied the 3 into this and used 3t plus 3 as my first and this as my second.
Can you still get it that way? Like,
Yeah. Yep. I mean, eventually you need to get it down to where you can put it all into one quadratic equation because you're going to have to solve it at some point. So. What else? 28 tells us that we have time is measured in days here, greater than or equal to 0. The rate of growth of bacteria population is given by a differential equation, dy dx equals ky. And it says y is the number of bacteria present, k is a constant, initial population is 1500. It says the population is quadrupled during the first 2 days. And the question is, by what factor will the population have increased during the first 3 days? Alright, so we've seen these this type of differential equation. This is probably our most common type. We know that it's going to lead us to the continuous change model, which is y equals y sub 0 e to the kt. And we know that in our case that 1500 is our initial. And it says that the population quadrupled during the first 2 days. So that means that, wouldn't that be 6,000 then? True. And so we get 4 over here equals e to the 2k. If I do the natural log of both sides, I get ln 4 over equals 2k. So I get 1/2 ln 4 equals, okay? Alright, and so that means that 1500 e to the negative, or e to the 1/2 ln 4 t would be our model. Alright, now if that's our k, here's what we need to see if we can figure out is what's going to happen if we do the first 3 days here, because we want to know how big a factor did it grow by. Well, if we could figure out y after 3 days, then we could figure out by how much it grew, couldn't we? Instead of quadrupled, maybe it's multiplied by 8 or 16 or whatever the case may be. So bottom line is, can we solve this sentence then with 1/2 ln 4 times 3? Well, where could this 1/2 go? It could go up as an exponent if it did. Wouldn't the e and the ln be composed with each other? So that means we'd have y equals 1500, and then we'd have ultimately the e and the ln would cancel out. We'd have the square root of 12. All right.
why is the 3 like inside the outline?
It hasn't been over 4 times.
Oh, you're right. Sorry. All right. That's exactly right. So that's not right then. So doing this would just give us, if I just did this part right here, from the e to this part, if I did the 1/2 up here, it'd be just simply ln 2. True? And so if I had e to the ln 2, then this part would be what? E to the ln 2 would be just 2. Okay. So how does the 3 factor in there? Let me write this a little bit bigger so we can straighten it out. Ultimately, we have 1/2 ln 4 times 3. So that's what we're looking at right there. So the question is, how do we simplify that? Alright, well, if we do, and again, keep in mind that ultimately this whole thing is the power on E here, so we can't just disregard the 3 for the time being and do something with this. So if we do the 1/2 part, we could rewrite that as ln 2 times 3. And remember, that whole thing is through power.
Like we take the square root of 4.
Yeah, 4 to the 1/2 would be 2. And then ultimately this 3 right here, if that 3 was written out in front, couldn't we put the 3 as a power also? So if we did, we'd have ln of 2 to the 3, which would be ln 8, wouldn't it? So that 3 times ln 2 is really ln 8, because that 3 can go up as a power. So had I written it as 3 ln 2, then that 3 can go up here as a power. So really I have e to the ln 8 there, so what is e to the ln 8? 8. And if I do 1500 times 8, that's going to give me my final answer for y. So what is the factor itself? The factor is 8. Questions on that one? What else? 25 through 30. Now number 30, we have, it says the region enclosed by the coordinate axes, the line x equals pi, and the curve cosine of cosine x is rotated about the x-axis, and what solid is generated. So this is a calculator problem. Keep in mind once we get to number 29. So if we were to take a look at the graph here, cosine of cosine x. Get that. And they said the coordinate axes here, so that, I'm going to make this y get a little bit smaller so we can actually see it a little bit better. So essentially that's our curve, and we're going to do, again, it says this curve, the coordinate axes, and the line x equals pi. So if I have my x equals pi over here like this, I essentially have, something like that, whatever. And bottom line is we're going to revolve this around the x-axis. So would a vertical slice work? Got the same top. The cosine x is always the top. The bottom is always the y-axis. So if that's the case, and I go, and this is my revolving line, the x-axis, that's going to make discs. So if I go 0 to pi, and my integrand here is cosine x dx. And remember what we want to do with that cosine x is square it. So our general setup for disk method is pi r squared for each disk. And that would be our setup. And then how much time should we spend on anti-differentiating that? None. It's a definite integral. We don't use any time for that. So do not waste your time on that. Just go ahead and go to your Math 9. Cosine of cosine x. And we get that, and it says all the decimal answers, don't forget to multiply by pi. And, oh, I forgot to square it, that's why. Try that again. This whole thing needs to be squared.
How do you enter stuff in your calculator without like overwriting?
Yeah, you use your second delete button.
Above your delete on the top row, hit second insert. Alright, that looks better. And times pi, 6.04 then, the nearest thousandth as they have it. Okay. Others? 29 just says that the average value of the continuous function on the closed interval is 12. And we want to know what is the value of the integral. Well, remember, in that integral, we would know that 1/4 of that integral equals 12 then, wouldn't they? Didn't they tell us the average value of f? And wouldn't this be the average value of f? And so ultimately, if that's the case, then we just want to know what this equals then, don't we? So to get that alone, couldn't we just multiply by 4? So we get 48 if we multiply by 4. The key issue is, notice that the average value of f is just the integral on 3 to 7 times the length of the interval, or divided by the length of the interval. Okay. So if that stuff equals 12, then we know that the integral itself had better have been 48.